Using inverse functions. So an inverse maps the output values back to their original input values. This means that the domain of the inverse relation is the range of the original relation, and the range of the inverse relation is the domain of the original relation. So if we were given this table of values, at the inverse, we just swap it. Whatever was x becomes y, whatever was y becomes x. So instead of the point negative 2, 4, it's now the point 4, negative 2. Instead of negative 1, 2, it's 2, negative 1. 0, 0, we swap, but you can't tell. And then it becomes negative 2, 1, and negative 4, 2. So x becomes y, y becomes x. The graph of an inverse relation is the reflection of the graph of the original relation. The line of reflection is y equals x. Because when we have points where x and y are the same and we swap them, we can't tell a difference. So that's the line about which the two graphs are reflected, and any points on that line stay the same. That's where the two would intersect. So here we have a cubic polynomial. And so we're just going to read off these coordinate pairs that we have here to fill in our table of values. So this coordinate pair right here is negative 7, negative 6. The next one is negative 5, positive 1. Then it's negative 3, 2. Then it's negative 1, 3. And then it's 1, 10. So for the inverse, we swap those points, and we have negative 6, negative 7. The x value becomes y, y becomes x. And then we're going to plot these points to find out what the graph of the inverse function looks like. So if I plot negative 6, negative 7, we're right here. 1, negative 5. 2, negative 3. 3, negative 1, 10, 1, and then I sketch in my graph. So this is actually the first graph of a cube root function that we're doing. We're going to spend an entire day talking about how to graph square root and cube root functions, but there's your first one. And we see that they are reflections of one another about this line y equals x. So if we would fold it over the line, everything perfectly matches up and they intersect right there on the line. So if we need to graph the inverse, that's the quick way that we do it. Once we have points for the original, we just swap them, plot those points, there's your inverse graph. Now if we want to find the equation of an inverse, we have 3 steps. So the first thing is, if it's in function notation, we want to switch it out to y equals. So remember, function notation is when we have like f of x equals. Oops. So we want to change that to just be y equals. It's easier to swap x and y than x and f of x. Step 2, we will swap x and y. So every place there's an x in the equation, we're going to write y, and in place of the y, we'd put an x. And then step 3, we resolve for y. And then notationally, when we put a little negative 1 on the y, that's our shorthand notation for inverse. So at the end, we'll either have y inverse, so y to the negative first, which means y inverse equals, or if it was in function notation, we should go back to function notation and say f inverse of x. But again, this little negative 1 exponent is the math symbolism for inverse. It comes from the idea that a negative exponent means to take the reciprocal, and reciprocals are multiplicative inverses. When we multiply them, they cancel each other out to give us 1. All right, so we'll change the function notation if we have it to y equals. We'll swap x and y, we'll resolve for y, and in the end, we'll put our little negative 1 to symbolize that we have the inverse equation. All right, so number 1 does not have function notation, so I'm ready for step 2. I swap x and y, and then we resolve for y. So instead of y equals, it's now x equals 3y minus 5. to start working my way towards y, I'm adding the 5 to move it over to the left-hand side. And then we're going to divide by 3, so it's up to you whether you keep it all together or if you individually divide and say 1/3, forgot my x, plus 5/3. Either is fine. And then remember, we put that little -1 on the y to symbolize that it's the inverse equation. All right, number 2 is given in function notation. So first step, swap the f of x equals to be y equals. And then replace y with x and x with y. And so we'll add the 3 to move it over. To cancel out the 2/5, remember we don't divide by a fraction, instead we multiply by its reciprocal. So we're going to multiply both sides by 5/2. So we'll have 5/2 x plus 15/2. Remember, when you take a fraction times a whole number's denominator is a 1. So we do the 5 times 3 to get 15, 2 times 1 to get 2. And on the right side, we'd get 10/10, which is just 1. So we solve for y, but again, because it was in function notation initially, we should go back to that and say f inverse of x equals the 5/2 x plus 15/2. And there's our inverse equation. All right, so those were both linear equations. Now we're going to take a look at a quadratic. So we're finding the inverse of f of x equals x squared minus 1, given that x has to be greater than or equal to 0. So the reason that they're telling us this is because if we think about a parabola, it's this U shape, and if we would reflect that over y equals x, we're going to end up with a parabola on its side, what we call a sleeping parabola. And the problem is it will fail the vertical line test. There'll be 2 outputs for any input, which would make it not a function. And we want to find a function. We want it to have 1 output for every input. So to make that happen, we restrict the domain. We ignore half of the parabola so that when we reflect it, we only have half, and then it would pass the vertical line test. And so this will need to happen for any even polynomial that we could give you. We've got to restrict that domain so that we only have half of the graph, and so its inverse passes the vertical line test and is in fact a function. So what it means is we're only going to use x values that are 0 or larger. So we're going to start with 0, 1, 2, 3. So our equation is x squared minus 1. So if I square 0, I get 0. Minus 1, it's -1. If I plug in 1, 1 squared is 1, minus 1 is 0. If I plug in 2, 2 squared is 4, minus 1 is 3. 3 squared is 9, minus 1 gives us 8. And so I can go ahead and plot those points. 0, oops, forgot that it's down at -1. There we go. 0, -1, 1, 0, 2, 3, and then 3, 8. So here's the original parabola, again, cut in half because we restricted the domain. So now to find the inverse equation, I'm going to first replace my f of x with y equals. Now I'm going to swap my x and my y, and we're going to resolve for y. So I'll add the 1, and then we need to square root to undo the square. And normally when we do square root, we always have to put down plus or minus. But because we have this domain restriction right here, we have to restrict here. So because this is the positive case, bigger than or equal to 0, we're only going to keep the positive case. And so we're going to toss out that negative case. And I'm going to go back to my function notation and say f inverse of x equals the positive square root of x plus 1. If this had said less than or equal to 0, so if they had restricted to the left side of the graph, then I would have kept the negative square root. But because they're restricted to the greater than or equal to 0, the positives, I keep the positive case. Okay, so we're going to graph the inverse, the square root function. This is our first square root graph we're going to do. And again, I'm just finding these points by swapping here. x becomes y, y becomes x. So negative 1, 0, 0, 1, 3, 2, 8, 3. I could have strategically chosen some x values and plugged into the equation, but I don't need to, because I know the relationship between inverses is that x becomes y, y becomes x. They work in opposite directions. So now I have my points, I plot them. Negative 1, 0, 0, 1, 3, 2, and 8, 3. And so there's the graph of the square root function. Again, that's our first one we're doing. We're going to spend an entire period talking about how to graph them. But there's the basic shape. And I just want to show you here's y equals x. That the two are reflections around, and they intersect right there on that line. All right, so now we're going to describe these graphs in terms of their domain and range. So for my original equation here, so it starts here for x, which is 0, and it's continuing to the right. So domain is bracket 0, since we actually have a point there, to infinity. For the range, lowest it goes is right here, which is negative 1, and then it's continuing up forever. So we say bracket negative 1 to infinity. We see the x-intercept right here. It's touching the x-axis at 1, 0. X-intercepts have a y value of 0. And then the y-intercept right here, where it's touching the y-axis, that has an x value of 0. So that's at 0, negative 1. Now if I find the same information for the inverse, which would be the square root, we see domain starts right here at negative 1, and it continues to the right. So we'll say bracket negative 1 to infinity. For the range, lowest it goes is the x-axis, which is a y value of 0, and then it's slowly but surely heading up. So bracket 0 to infinity. The x-intercept we see right here has a y value of 0, negative 1, 0. And then the y-intercept, where it touches the y-axis, right here, or in the table, x value of 0, so 0, 1. And what you should see in this little chart is that the domain became the range became the domain, the x-intercept became the y-intercept, and the y-intercept became the x-intercept. So we're seeing that inverse relationship where x becomes y and y becomes x, and everything swaps. All right, so now we have just some harder equations to find the inverse of, some more Algebra-like type problems. So remember, step 1, replace f of x with y. And then we're going to resolve for y. So we're going to subtract the 5 to move that over to the left-hand side. Oop. I forgot to swap my x and my y. I replaced the f of x with y, but now I got to swap the x and y and have x equals 4 times the cube root of y minus 1 plus 5. Now I can start solving for y by subtracting the 5. So we've got x minus 5 equals 4 times the cube root of y minus 1. And so we'll divide by 4. And I do recommend you keep it together here because in this next step we're going to raise it to a power, and it's going to be a little bit easier if we keep it all together. All right, so to cancel out the cube root, remember the opposite of any root is its corresponding power. So we're going to raise it to the third power. Now we have to raise everything in the top and everything in the bottom to the power. In the top, you have a binomial. So if you want to raise that to the third power, you would have to write it out 3 times and go through and do your polynomial multiplication. Multiply these first two together and get x squared minus 10x plus 25 when you do FOIL or a box. And then if you take that times the x minus 5, would get x cubed minus 10x squared plus 25x minus 5x squared plus 50x minus 125. So we'd have x cubed minus 15x squared plus 75x minus 125. But we're not requiring you to do that. You can leave it. You are allowed to leave it in this unit like this, x minus 5 to the third power. But go ahead in the bottom and do the 3 to the third power. So 3 cubed is 27. You know, that part we should be able to figure out easily. Equals y minus 1. And then you can move. So if you want, you could write it as 1 over 27 times x minus 5 quantity cubed plus 1. And then remember, we should always go back to that function notation. So f inverse of x So again, you don't have to multiply this out. You can leave it, x minus 5 quantity cubed. You should raise that 3 that was in the denominator to the third, though, and have divide by 27, or write it as 1/27 times the quantity. But if you're choosing to multiply it out, you got to do it correctly. FOIL, multiply, or distribute property, or box. Multiply, combine like terms, times another one, combine like terms, and get this whole big polynomial. All right, so number 5, again, replace the f of x with y, and then swap the x and the y. Move the 2 over, so add the 2. And then we don't divide by fractions, we multiply by the reciprocal instead, so we're going to multiply both sides by 2, and get 2x plus 4 equals y cubed. And then we undo the third power by taking the third root. So the opposite of any power is its corresponding root. Make sure that 3 is inside the check mark right near that corner there, so that it's the index and not 3 times the square root. And that's going to equal y, but again, we should go back to that function notation and say f inverse of x. So if you have a cube root, its inverse is the cube raised to the third power. If you start with a cubic polynomial, its inverse is the cube root. Powers and roots are inverses. All right, number 6. So again, we start by swapping that g of x, rewriting as y equals, and then we're going to switch our x and our y and resolve for y. So I swapped the x and the y, added the 1 to move it over, and now I'm going to multiply by the reciprocal, which is 2/3. So we will have 2x plus 2 over 3 equals y plus 6 quantity squared. And then to cancel the square, we got to take the square root, which means we need to do plus or minus, because they didn't give us a restriction on the domain. And I'm going to go ahead and square root each one separately, because ultimately I got to rationalize that. So I'm going to go ahead and multiply top and bottom by square root of 3. So that'll have the square root of 6x plus 6 over whole value 3. Remember, we worked on that in previous sections of this unit. We cannot have a radical down here in the denominator. So as soon as I see I'm taking a root of a fraction, I know there's a problem. I've got to rationalize. So remember, you can take the square root of the top separate from the square root of the bottom, and then with the square root, to cancel it out, you just multiply it by itself. So we multiply top and bottom by square root of 3. Down here we'll get square root of 9, which is just whole value 3. Up here we can multiply because they're all under a square root, and so we get square root of 6x plus 6. And I'm going to finish by subtracting the 6 to the left-hand side. So plus or minus the square root of 6x plus 6 over 3 minus 6 equals y, but because it was in function notation, I'm going to go back to function notation and say g inverse of x. So we got to make sure in our final answers we're always rational for any denominators. All right, number 7, another cubic polynomial here. So I'll replace that f of x with y. I will swap my x and my y. And then we'll resolve for y. So we'll add the 5. So we have x plus 5 equals y plus 2 quantity cubed. To cancel out the cube, the opposite of any power is its corresponding root. So we'll take a cube root. Because it's an odd root, we do not need plus or minus. And then we'll subtract the 2 over. So we'll have the cube root of x plus 5 minus 2, and we'll go back to that function notation and say that's f inverse of x. So just be real careful when you're writing this that the radical bar stops well before the minus 2, or a lot of the times we'll put minus 2 first and say negative 2 plus the cube root so that it's clear this is not under that cube root. All right, number 8. Again, start by swapping that f of x with the y equals. And then we'll swap our x and our y. And we'll start solving for y. So we'll add the 2 to move it over to the left-hand side. And then I don't want that y plus 6 in the denominator, so I'm going to multiply both sides by it to cancel it out. You could also think of this as cross multiplying, like think of this as being over 1 and then cross multiply. However you want to think about it, but we will get to the point where we have y plus 6 times x plus 2 equals 1. So again, you can, whatever's in the denominator that you want to clear out, if we multiply both sides by it, it'll clear it out, because anything divided by itself is 1, and we're just left with 1 over there. And then you multiply by it on the other side as well to maintain the balance of the equation. Or think of it as a proportion. X plus 2 over 1 equals 1 over y plus 6. 1 fraction equals 1 fraction is called a proportion. And you can cross multiply. The cross products always have to be equal. So the y plus 6 times x plus 2 has to equal 1 times 1, which is 1. And so now that we're here, we want to divide by that x plus 2 because we want the y plus 6 term by itself. So we'll have y plus 6 equals 1 over x plus 2, and then we'll subtract the 6 to finish getting the y all by itself. And again, we'll go back to that function notation. So f inverse of x equals 1 plus x divided by 2, 1 divided by x plus 2, and then minus 6. And there's our inverse. So we'll try another one like that. So swap the f of x with y, then swap the x and y. So you have x equals 2 divided by y plus 3. And again, if you want to think of it as a proportion, just remind yourself whole numbers have a denominator of 1, so you can cross multiply. Or just think of it as fraction busting and multiply both sides by the y plus 3. Either way, you'll end up here. X times y plus 3 equals 1 times 2, which is 2. We're going to divide by that x to get that y plus 3 term by itself. So we'll have y plus 3 equals 2 divided by x. And we'll subtract our 3 to get the y all by itself. But because it was in function notation initially, we should go back to f inverse of x equals 2 divided by x minus 3. All right, a couple more here. So again, replace that f of x with y equals. This time we have multiple x's, so every place there's an x has to become a y. So we have y plus 2 divided by y minus 7. And so, again, think of it as a proportion. So realize x is really x over 1. This is a single fraction, so we can cross multiply. Or just think of it as multiplying both sides by y minus 7. However you like to think of it, we get to here. X times y minus 7 equals 1 times y plus 2, which would just be y plus 2. I can't just divide by this time because I've got a y over here as well. So I am forced to multiply this out. And then we're going to move our terms around to get all the y's on one side and everything else on the other. So I want to move this over here to join these y's, and I want this over there out of the way. So I'm going to add 7x to move that over here. I'm going to subtract this y to move it over there. So I will have xy minus y equals 7x plus 2. I couldn't actually combine anything because none of them were like terms. I was just kind of swapping sides. So moving this over to the left, so it's now minus y. Moving this over to the right, so it's now positive 7x. But on the left, I now have a GCF. These two terms both have a y, so I can use GCF factoring. I can divide out the y, and I'll have x minus 1 So then I can finish solving by dividing by that x minus 1. So that's what y would equal, but again, I should go back to function notation and say f inverse of x equals 7x plus 2 divided by the x minus 1. So one more like that so you can see it again. So always replace f of x with y. And then we're going to swap x and y. And again, think of it as cross multiplying or just clearing out the denominator by multiplying both sides by y plus 1. But we should get x times y plus 1 equals 1 times 3y plus 5, which would just be 3y plus 5. We have to distribute here so that we can move terms around to get all of our y's on one side, x's on the other. So we'll subtract 12xy minus 3y, and we'll move the x over here. So we'll have 5 minus x, or negative x plus 5, however you prefer. Now that we have, so again, we had to distribute here so that we could move these y's over to join those, and this x over there, so that we only have y terms on the left, everything else on the right. Since these both have a y, we can factor that out with GCF factoring. So if I divide by y, I'm left with x minus 3 equals 5 minus x. And then we finish by dividing by that x minus 3 to get the y all by itself. But because we were in function notation initially, rather than writing y inverse equals, we should write f inverse of x equals 5 minus x divided by the x minus 3. And that would be your inverse equation. So number 14 says, are any of the inverses above not functions? And remember, the issue with it being not functions stems from those even functions. So if we go back here to number 6, this is quadratic. This would be a parabola. And so remember, if we would reflect that over, because of this plus or minus, we've got this sleeping parabola on its side. It's going to fail that vertical line test. So number 6 is not a function. The rest are fine because odd polynomials, we saw the graph of those here. Its inverse passes the vertical line test, no problems. But for any even polynomial, and we've just looked at quadratics so far, we have to provide a restriction to cut it in half so that the inverse is a function. And number 6 did not do that. So number 6 is not a function. The rest are fine again because these are odd degree. They're going to pass. And we can, to figure that out, we can do a horizontal line test on the original. So we do a vertical line test to see if the original is a function. If you want to know if its inverse would be as well, try horizontal lines. If a horizontal line can touch in 2 places, then you know that inverse is going to fail. All right, so number 6 was the only one that's not a function because it's an even polynomial and its inverse would have 2 outputs for each input. All right, so how do we prove things are inverses? Composition of functions. So that is one of the reasons why we learned composition of functions. If we compose inverses, so we put one of the functions inside of the other one and fully simplify, all the operations should be opposite and cancel out and just leave you with x, the original input. But it has to work in both directions. So then we'd have to take the other function, plug it into the other one, again, simplify and only get x. When we compose in both directions, all the operations cancel everything out and just leave you with x, they are definitely inverses. If you get anything else, so x plus 1, 4x, nope, not inverses. So if we are asked to verify that these are inverse functions, that means to prove. And to prove it, we can't just find the inverse of this. We need to do this. You will be asked to do this on the test. And if you don't do it as we require with composition of functions, you will not be given credit. So the way we verify or prove that they're inverses is composition. We're going to take this, plug it in here in place of the x, fully simplify, see what we get. Then we're going to take this, plug it in place of the x, fully simplify, see what we get. So I'm going to first start with f of g of x, which means I'm going to put g of x inside of f where the x was. So function f says 3 times some input minus 5. So I left the x out, put a blank set of parentheses, because with substitution, remember we get rid of the original variable, and in place of it, put our new stuff. And our new stuff is supposed to be g of x. So I'm bringing all of this and putting it in place of that x. So 1/3 x plus 5/3. And now we simplify. So I'm going to distribute the 3. 3 is 3 over 1, so when I multiply it, it only affects the numerators. So I'm going to have 3x over 3 plus 15 over 3 minus the 5. Well, 3 divided by 3 is just 1x. 15 divided by 3 is 5. And 5 minus 5 gives us 0, so we're really just left with x. So it works in that direction. F of g of x, all the operations were opposites of one another, and so they all canceled out and left me with the original input of x. Now I've got to verify it works the other direction as well, so I have to do g of f of x. So function g says 1/3 times some input plus 5/3. So again, I left the x out because when we substitute, that goes away, and in place of it comes the new information. So I'm taking the 3x minus 5 and putting it in place of the x. And again, I simplify and solve, so I've got to distribute the 1/3. So again, remind yourself, whole numbers times fractions. Whole number only affects the numerator. So we'll have 3 over 3x minus 5 over 3 plus the 5/3. Well, 3 divided by 3 is 1x minus 5/3 plus 5/3 equals 0. So we really are just left with x, the original input. So when we ask you to verify that things are inverses, again, I cannot just take this, swap x and y, and solve for y and say, oh yeah, I got that. Nope. This is like asking you to do a proof, and the way we prove it is with composition of functions. That's one of the reasons why we learned this in a previous section. So you have to take one, plug it inside of the other in place of the x, and then you must step by step show your simplification process and why we really are getting back to x. And then you have to do it the other direction as well. So then we've got to take this, put it in here, got to do it both ways. And again, you must strategically, neatly, organized, show us step by step what's happening and how we're getting back to x. And as long as both of them just equal x, you get to say, yep, they are inverse functions. But if either of these would have come out to equal anything besides just 1x, then you'd say no. So there you have it, inverse functions, functions that are opposites.